That is a really interesting thing in that you can just do a replay attack as you did. And there are other really simple attacks that you can do without even having to understand anything below. So I mean, for a moment, if this were really cryptographically sound, it doesn't matter, right? Because you're still able to replay this.
Yeah.
You don't even have to know what the cryptography is. Some of these vehicles, they actually have other features that are built into the vehicle, like an alarm, for example. But the model of your vehicle doesn't have that. And it's not that it doesn't have that. It simply doesn't have the button for it in the key fob they've sold you. So if you flip that bit, you then activate that feature of the vehicle. As long as it has the hardware, and many of them do, for something like an alarm. So there's actually hidden features in a lot of these things, which is another kind of really just interesting area, I think.
Side note. Yeah.
As these cars get more advanced, and there's other really interesting attacks. So there's one I was never able to fully complete, but if you listen to FM radio, or maybe you used to listen to FM radio in the vehicle. And FM radio is just frequency modulation, so it's just waves going like this, essentially an analog signal. But have you ever seen the FM radio where the name of the song would play? It would show you the name of the song? Yeah. Okay, but how are they getting that to the vehicle? Now, FM radio is an analog signal, right? So it's not actually in that song, and it's not like your car has Shazam built in. So there's another protocol called RDS, and this is a digital protocol that sits outside of the FM band. So it's like on the outskirts of the band. So you have this FM modulating wave, and then up here is a digital signal with information about what you're playing. So I was playing with that, and first I was just messing with people and saying whatever I want on the radio.
That's cool.
But then I was thinking, okay, well, we have digital information here, and I found a vulnerability within an RDS interpreter, within an RDS system. And what's cool there is that if you can exploit RDS on a car's informatics system or telematic system, basically the radio that's connected to everything else, well, you're then connected to the radio, and the radio is connected to the CAN bus, which is connected to everything else, like the veins of the car, and that's where signals are going. And in modern vehicles, if you have something like assisted parking, where it can turn the wheel for you and hit throttle and brake for you, well, those are also connected to the CAN bus, because you might push a button on the steering wheel and say, hey, help me with assisted parking. And then the car takes over and you let it park for you. But that's connected to the telematics system. So all through the CAN bus, that same bus. So if you can hit and you can exploit any one of these systems, then you now have access to basically everything else in the vehicle and any other components that it has, because you're essentially a trusted device. Though, like, the radio is trusted. Like, there's no authentication, there's no users or passwords once you're talking CAN. So it's definitely an interesting area of attack. And Charlie Miller and Chris Valsek were able to do a very cool exploit demonstration of this many years ago on a Jeep, and they were able to take over the system over the internet and control the vehicle.
That's crazy.
Yeah, it's absolutely nuts. I mean, it's super interesting because I can see why I believe it will be beneficial for us to actually have these computers take over. I think computers are going to be better drivers than us, even if there are vulnerabilities. I think statistically they will be better. Many of these vehicles these days, they have something called passive entry and start. And what that means is passive, as in the owner of the car, the person with the key. They don't have to pull their key out of their pocket or bag. You put your hand on the door and maybe there's capacitive touch or a button, but it unlocks. And then you go inside the car and it's not the same thing, but you press a button to start the vehicle. You don't turn a key, right? There's no physical key turning or physical removal of your key. The key is on you. It's somewhere inside the vehicle, and it can detect that. And what's happening there is that your car is constantly emitting a low frequency signal, either 125 kilohertz or 134 kilohertz. So that's actually similar. That's actually the same frequency as RFID. If you've ever taken like one of those old badges and you've waved them. So that it doesn't go very far. They're active transmitters, but they'll go a couple meters maybe. And your key fob will pick that up and say, oh, I see the code that's coming through this. I know this model vehicle. And if it sees that, then it will respond, hey, I'm this key ID 1234. And if the car says, oh, I know 1234, then it will ask you a challenge again, over this low frequency 125 kilohertz, and your key fob will then wake up and respond to that challenge. Maybe it'll send some random data and it says, hey, encrypt this to prove who you are. And you encrypt it with your key, which is shared with the car. And you then transmit it back over UHF, so 433 megahertz or 315 megahertz. And the car, if it's like, oh, that's legit, then I will unlock the vehicle. It also does some RSSI, or receive signal strength indication checking. So just to make sure that the key fob is close enough to the car, to the vehicle. So you don't, because it's possible for the key fob to respond from far away. And the car says, well, you're not close enough yet. I'll unlock when you're closer. But what's interesting is there's nothing really preventing you from relaying that information. So let's say you're in a coffee shop, right? And your car is outside, much too far for the communication to go back and forth. But an attacker like me comes around and I go up to your car and maybe I have a device. And that device is very similar to roll jam. You just need literally use one of the extra pins and a coil, and you now have essentially this relay device. And that picks up the low frequency signal, and I'll need a friend. And a friend will go inside with an identical device. And all I'm doing is I'm then taking that low frequency signal, which only travels a few meters, and I upconvert it to 433 megahertz, 2.4 gigahertz, it doesn't matter. Something that can go far. I can send it over cell phone if I wanted. And it gets sent to the second person who's now sitting in the coffee shop near you or near your key. And then they pick up that signal because it's transmitted over a much longer distance communication protocol. They bring it back down to low frequency. It travels a few meters. It hits your key fob. Your key fob says, oh yeah, I know this model vehicle, and it responds. And the same thing happens. The communication just goes back, and you do this twice. And by twice, we're talking about hundreds of milliseconds. You're not doing anything, right? It's just the devices are just communicating because they sense each other. We're just doing it over a much longer distance. And that will unlock the vehicle. And the attacker can then get inside the vehicle. Same thing for the key, for the button. And now we talked about the signal strength indication. We have to make sure that the device is close, but it doesn't matter because the thing that is transmitting at the end of the line inside the vehicle is right in the vehicle, right? It's this device that is simply it's a transmitter and a receiver, like at the end of the day. So that's how many cars are being broken into, stolen. And it's actually really bad because insurance companies are saying, you file an insurance claim, you say, hey, I locked my car and all my stuff was gone. And they say, well, was there any forced entry? Like, did anyone break a window? I say, no, my car was unlocked. I said, oh yeah, you probably left it unlocked. But that's not what's happening. I'm like, so it's a challenging problem. I mean, there are interesting ways that people are trying to solve it. Ultra wideband is one. I don't know if that will actually ultimately solve it because I think that can fall for the same attack. But I did see something interesting recently. I think it was in the last year that one of the car manufacturers added, and it's a clever idea. I think there's a way around it. They added either an accelerometer or a gyroscope to their key fob. And this is to prevent the relay attack. And the idea is if your key fob isn't physically moving, it shouldn't respond.
Yeah.
So you're in the coffee shop sitting down, right? You're reading a book and probably a really interesting science book. And the key fob is sitting on the table and it's not responding to the attacker who's sitting there nearby. And I thought that's a pretty clever idea. Yeah. But there was an interesting paper a couple of years ago, and it was talking about how to fool drones, how to make a drone believe it was somewhere else. And I was working on some drone exploitation, mostly in RF, investigating sort of GPS spoofing and breaking the cryptography of the communication links for the telemetry of drones for the RC transmitters, as well as they typically have separate telemetry hardware that allows them to communicate where they are and what they're doing. But these researchers were looking at how can we fool a drone, not with the RF, but rather with the IMU. So the inertial measurement unit, which is the accelerometer, gyroscope, and magnetometer, because that's what tells the drone, oh, I'm a little bit tilted. I need to turn on these motors on more to get back into balance. That's how we can have such cheap drones, is because we have these IMUs that can tell us here's where you are essentially in 3D space. But all of these essentially have resonant frequencies inside that have resonant frequencies like everything. And if you can hit those MEMS gyroscopes with ultrasound at the resonant frequency, you can make it believe it's in an orientation that it is not.
Oh, wow.
So essentially with pressure waves, right, with sound waves that humans wouldn't hear, like ultrasound, we won't hear that. And you can get some ultrasonic transducers. They're very small. No one would know what's even happening if you're in the coffee shop playing ultrasound, and you're just waking up all of these key fobs because they think they're moving now. I haven't tried it, but I'd love to test that out.
I mean, you're essentially a man in the middle, right, with the relay. Could you just add the gyroscopic information? Oh, I suppose they'll be encrypted though when it's.
Well, I believe the key fob is not responding in the first place if it's not moving.
Oh, okay.
Right. So your key is sitting on the table and it's saying,
course,
I see my car, but I'm not going to ignore it because I need to move first.
No, that makes sense.
Because why is Steve trying to open me while he's sitting down? Doesn't make sense. You want to fool it to think, oh, no, Steve's done with his coffee,
I mean, what you really want is a key fob that says, well, hold on a second. It doesn't make sense for a car to be in a coffee shop.
Yeah, that's good. I mean, that's actually a really cool idea, Steve. No, let's think about that for a moment. What if your key fob is synced to your phone over Bluetooth? Then you get the advantage of the GPS and other location services and assisted GPS using Wi-Fi signals from your phone. So as long as you have that BLE communication, then you could be in call it a convenience mode. So as long as your phone's on you, you're in this convenience mode, which adds that layer of security by testing the location based off your cell phone. Now, if you forget your cell phone, that's okay. You can pull out the key and press the button or something, right?
Yeah.
Through some additional action that doesn't leave you, in the lurch if you forgot your phone. Yeah. So that's an interesting idea.
Yeah, it could work, I suppose. Yeah. I mean, you as a consumer, you then have to pair your car key with your phone, and you don't exactly know why you have to do it. But I mean,
that's a good point.
Yeah.
It's funny, some of the key space for some of those rolling codes were so small in vehicles earlier that people were finding that they would unlock and someone else's car would unlock too. If you're in a crowded parking lot.
Presumably in the early days you could do a brute force like you did on Derek's garage door. I just saw it. That's great.
Yeah. You could do brute force. Probably that specific attack of the De Bruyne sequence probably wouldn't work because there's other data. But yeah, absolutely, you could do brute force.
It would take a little longer, but yeah, I mean, if you've got all night essentially.
Yeah, and if you're in a crowded lot, it doesn't matter which one opens, right? You just keep one of them. It's kind of interesting, especially with these attacks. Like one thing that I'm hearing here, at least in the US a lot, is that people's cars are getting broken into, and the thing that's getting stolen the most, because all vehicles have it, are the airbags, and then they get resold.
Really?
Yeah, apparently airbags are expensive. Like to get a certified, legitimate airbag, that's a very expensive piece of equipment. It probably has to go through, some sort of UL safety testing or whatever safety testing that they might do. So the resale value on those, and every car has them, right? You're gonna, unless someone knocked that car earlier tonight, stole it before you, you're gonna at least get a couple of airbags out of it. It's kind of crazy. I mean, it's terrible because obviously it's a safety feature, and at least most vehicles do have a sensor, so when you start up your vehicle, it says there's no airbag detected. So that's good.
What do you think about the process? This is a philosophical question about as a security researcher, finding a vulnerability and publishing the vulnerability. Like, what's the process? I guess the feeling is like, by publishing it, you're making people safer because, it's no longer an undocumented expert. It's no longer like a 0 day or whatever, right? People know about it now. But you're also making it public for people to be able to exploit that. How does that shake out when you're looking at the moral landscape of security research?
Yeah, absolutely. I mean, that's a great question. Definitely one I struggled with earlier on. I guess I didn't struggle with it. I guess I was unimpressed that I would share what I thought were sort of big issues that were potentially already being exploited by malicious actors. And in many cases, I knew they were being exploited by malicious actors, and I would share that privately with various companies. And to this day, I still do. If I believe this is a big thing that can easily be exploited by people, and will do more harm than good, and can be, let's say, maybe difficult for a manufacturer or someone to solve, but easy for people do, then I probably won't release that. So like I haven't been releasing, say, the relay and amplification stuff I've been working on because it's too easy. It's actually like, unfortunately, it's very easy. But there are things that I do release. And what I found is that often if I'm just privately communicating with some vendors, and this is not all companies, this is, and fortunately over the past, call it 5 years, things have shifted a lot. People do really understand that cybersecurity and just security in general is important. So companies are much more open to understanding the vulnerabilities and working towards a mitigation plan within a reasonable time frame. Usually 1 to 3 months, I think, is reasonable. And yeah, I think it depends. So I find that sometimes you'll demonstrate something, and if no one hears about it other than the company, oftentimes nothing happens. And personally, what I'll do is I might release a simple thing, like a very simple tool, not like too technical for like modern for anyone to even realize what's going on. But I'll reach out to the company, I'll share with them, and if it's not fixed, like I'll return a couple years later and I'll release a new version. And I think I'll make it a very interesting, well-documented, fun, like just something that's fun for me to then share with other researchers to understand, hey, here's how you can find these types of vulnerabilities as well. Because there are a lot of clever people out there who can find new things as well. And then I'll make it sort of maybe a big project that you can just download off GitHub and you can use, because I know it's not that will force a company's hand to resolve it, but it's the public saying, hey, why is this vulnerability here? And they might be upset at me, but I already know I've already shared this information years ago. I'm talking like literally years. So this is often how my bigger projects will come about, where I typically do share something privately or to the right technology folks. And I think it's on a case-by-case basis. It really just depends. Like I don't want bad things to happen to people. I'm trying to, I think, it comes down to a little bit of it's a bit of a question of maybe that philosophical question of like, you may not even be the conductor of a train, but a train is going to go down a track that might hurt some people, and you can change it and maybe hurt less people. Honestly, at the end of the day, there are people who are using these things. Like the relay attack, there was a paper on that came out 9 years ago. 9 years ago, we're talking in the public domain. So it's not that this is a secret. It's and to this day, cars are being sold with that same technology. So
that's crazy.
There's a lot of things at play here, and I understand it's difficult to change. It's not like, hey, we need to stop car manufacturing. Like you can't just do that. So I understand there's a lot of complexities there, but yeah, I do think there's a checks and balances, and everyone has their what they believe is important to them, and I think everyone should sort of execute on their area as long as they feel that it's ethical.
Yeah, I mean, that sounds like the right way to go about it, but it must be an interesting question in your mind every time you find something new.
It is because there's definitely things you want to share. Like there's definitely
because it's so cool.
Awesome. Yeah. I've been getting more into how can I don't want to attack what systems. I don't want to attack things that humans have made anymore. I want to really understand how can we do. I'm much more interested now in side channels. So exploiting properties of physics that we didn't quite understand, or that physicists understood, but maybe technology people did not. For example, if you're encrypting something on your computer, you're generating, you're using power to encrypt. Whether you're encrypting a 1 or a 0, you're going to take different instructions, and those instructions will take more or less time or power. And your CPU itself is pulling power for those instructions, and the capacitors around are pulling power, and those are running to the electrorestrictive effect, and they're physically moving. You and I can't hear them moving because they're producing ultrasound again, but something like our phone, like a cell phone, can. So the cell phone bandwidth, the frequency goes up to ultrasound, so it can pick that up, and if you can record and then look at that information, you can then reveal the key or information that was being encrypted, and the key that you use for everything. So this is, I would never blame someone for doing this. No one knows. No one knows that this is happening. It's really only when you can put these different pieces together and take a lot of this information and then be able to reveal, oh wow, your computer is screaming secrets. It's absolutely, it's really incredible. So I'm definitely more interested in those types of attacks, or same thing with these single upset events, like high energy particles that have caused supposedly plane crashes.
Yeah. bit flips.
Bit flips, exactly.
Because there's just this slow creep, isn't there? I mean, we're at the end of it now, but basically there's a computer between every single part of the car and you. And that's just happened slowly over the years. Like, there's now a computer between the accelerator and the car. There's a computer between the brake and the car, the steering wheel, everything. Yeah, but so the cosmic ray turns up, it flips a bit somewhere, and you can't brake or whatever the issue is.
Yeah, it's insane.
But
so I've definitely been interested in high energy, really controlling systems. Like, can we inject high energy particles, right? Can we produce that and cause a system to behave in a way that it wasn't intended, positively for an attacker?
As a complete tangent, when astronauts first started going into space, they would get these just flashes of light in their vision, and no one ever said anything until one astronaut said, I occasionally get these flashes of light, and the other astronauts were going, God, yeah, me too. And it's just when a high energy particle, because they're not protected by the atmosphere, a high energy particle reaches the back of their eye, and it's just a flash of light.
No way.
Yeah.
That's so interesting.
Imagine that happening to a sensitive component in a computer. The smaller the components get inside your computer, the more vulnerable they are to these high energy components.
Wow, that's really interesting.
With the control systems in a car and a spaceship, for that matter, they're supposed to have all this fallback and all this kind of redundancy built in. But I guess it's really hard, to protect against something like that. But you'd hope that if a bit flips over here, well, actually, you've got 3 other copies of it, and they win the argument because there's 3 of them and one of you. But I mean,
right, and I think that makes a lot of sense in the unintentional bit flips.
Yeah.
But when you start looking at intentionally doing this, then you're talking about a different set of rules, right? Someone can say, well, I understand the system uses 3. Hey, I only need 2 transmitters now.
Yeah. I just need to turn up the power on my accelerator.
Right. Yeah. So I have a project in progress right now, which is building a simple cloud chamber, because I want to view the high energy particle while it affects a chip inside, and then validate that it was changed both optically and electrically.
I tried to build a cloud chamber and didn't have much luck. And then just randomly, one of my subscribers, what's that?
Was the cooling the issue?
I honestly
was it just getting it to temperature?
It might have been. It was just a little desktop thing, using dry ice and IPA, isopropyl alcohol and stuff. But I mean, it might have been. I did try it outdoors, but I was surrounded by these buildings with metal roofs, and it may have been that. But someone actually just randomly emailed me and said, "I've got this particle, the cloud chamber. If you ever want to use it for videos,
awesome.
I have that at my disposal."
Oh, that's really cool.
But I mean, if you ever wanted to collaborate on something like that, that'd be awesome.
Oh, I'd love to. Yeah, I think that'd be a lot of fun. Especially, with your knowledge. I mean, I'm literally going through like physics 801, like the entry level physics course through MIT OpenCourseWare, just to learn some.
Oh, that's cool.
I didn't go to school, so I'm trying to learn this. As I try to go lower and lower in the stack of technology, I'm now at the lower. I need to know physics now. Right, because now everything is really just electrical components and charged particles moving through conductors. So I was reading about the cloud chamber and how it was created. Apparently, you probably already know this, but I just thought it was super interesting. I read it yesterday, where they believe that the particles, these high energy particles in the cloud chamber. For one, the cloud chamber had nothing to do with high energy particles. They were trying to do something with clouds. He was literally trying to reproduce something with clouds. Yeah, hence the cloud chamber.
Yeah, of course.
And they thought, the physicists thought, that the particles were coming from the Earth.
Yeah.
So they're like, oh, well, to validate that, we'll go in a, easy to test. We'll go in a balloon, in a hot air balloon. And they went to a hot air balloon, and the higher they got, the more it happened. Like, what? It's coming from space. That's so cool. It's just wow. I love that.
Yeah. My son is 3 years old, and I don't know why, but I had the lid off the tank, the cistern of my toilet,
Okay.
and he was looking inside, going, "Oh my god!" And we spent about half an hour just looking at how the system works, pulling the handle and watching the water going down, all that sort of stuff. That I think he's got that same thing of me. He just wants to know how everything works, which is cool. But
That is really cool.
key cards, RFID key cards.
Oh yeah,
because
terrible.
yeah, I mean,
Oh, it's
incredibly
terrible.
bad, right? Because
So there are new ones that are good, but they're not great.
Because they're mostly fixed code, right?
The old ones. So
Old
the
ones are
problem is
fixed
the
code.
old ones are ubiquitous. They're super
Yeah.
ubiquitous, right? They're typically called they call them proximity cards, and those are the low frequency 125 kilohertz. And yeah, all you have to literally you can take a microcontroller, like you can take an Arduino, and you can generate 125 kilohertz. You don't even have to generate a sine wave. You can generate a square wave. It's fine, and put it on an antenna, and that will wake up, and that will cause the card to then return its fixed code, its fixed password over that RF. I mean, it's backscattering, so it's collapsing its own antenna to transmit a 1 or a 0 back, and then you just record that, and you've copied it. You don't even need to touch it, right?
Yeah.
You can steal somebody's information from meters away by having a strong enough field. Receiver.
Because we've got contactless payment cards, right? I guess you've got them in the US.
Much better. Those are we do finally
because you've got that technology, and surely that's going to be something like a challenge response.
Correct.
It must be fairly easy now to put that into just an ID card for a door, so that it's a challenge response kind of thing. But then I guess you have to upgrade the door and everything. You have to upgrade the reader and everything, so it becomes
that's it, right? So there's a couple things. It's the proximity cards are cheap. Right, so you're talking the costs. When companies buy them, for example, they're paying very little. Where you're talking the smart cards are a bit more expensive, not terribly, but reasonably. But yeah, you have to upgrade the reader, right? And that becomes a challenge.
Maybe I said this in an email, but I first came across you when I was listening to the Darknet Diaries podcast.
Oh, cool.
Were you interviewed on that, or was he just telling a story? Yeah, you were interviewed on it, weren't you?
Yeah.
But yeah, he does a lot of physical pen test stories, and they're so fun as well.
Yeah, they are.
People get into buildings and stuff. It's so fun.
Yeah, it's super interesting.